All right, so today we're going to go ahead and continue looking at our definite integrals. So first off, can someone remind me, what was a definite integral representing, however you want to put it, graphically, geometrically, something like that? What did my definite integral sort of represent? Yeah, so the definite integral had a lower bound and upper bound and then a function. And then geometrically, it represented the area, quote unquote, under the curve. We said quote unquote under because if it's above the x-axis, it was under. If it was under the x-axis, it was above. But you'll often hear most people just say the area under the curve. That I guess a more accurate description would be the area from the curve to the x-axis. All right, so we're going to continue looking at that. And in particular, we're going to look at a very important part of calculus, the fundamental theorem of calculus. So, as you can probably tell from the name, what does fundamental usually mean, more or less? For fundamental, pretty much a very big, what was that? Basic, the important stuff. Basically, this is going to be one of the big foundations, especially for those of y'all go Cal 2. All right, so let's go ahead and first introduce the fundamental theorem of calculus. And actually, I'm going to split it into two parts. So I'm going to have a part 1 and then a part 2. So part 1, our theorem for first theorem for today, the fundamental theorem of calculus part 1. Assume that I have a function f that is continuous on a closed interval a to b. So I have a function on an interval from starting from a to b. I can trace the entire function without having to lift my pencil, for example. If I have an antiderivative of that function, so let's call my antiderivative, one of my antiderivatives to be capital F of x, of little f of x on this interval. Then, if I want to look at the definite integral, we know that this is usually the area under the curve. That's how we first introduced it. This is equal to my antiderivative. And then I'm using this notation. It kind of looks like a line from A to B, which in notation terms actually just means capital F of A minus capital F of B. So now actually this theorem is relating what we knew about the indefinite integral and the definite integral. Again, the definite integral, we said that we introduced it as area under the curve. We introduced integral as also the antiderivative. So in other words, this fundamental theorem of calculus is saying that if I want to evaluate this definite integral, I need to get the antiderivative of the function. I then plug in the lower bound and then the upper bound. Oh, and I actually made a mistake here. This should be f of b minus f of a. That is a very big mistake on my part. F of b minus f of a. Upper bound minus the lower bound. Well, this is, remember this little squiggly line, the integral says I want to integrate it. I want to get the antiderivative. So whenever I get the antiderivative, that's capital F, this straight line is indicating I want to plug in upper and lower bounds. So squiggly line means we need to integrate, get the antiderivative. The straight line, you can think of it as meaning now I need to plug stuff in. Also remember, whenever we draw this integral symbol, we usually like to think of it as a package deal, the integral and dx, for example. So again, this is relating what we know about how to get some antiderivatives, and we know what the geometric representation of the definite integral is. So this can lead us to a conclusion that the antiderivatives help me find area under the curve. Because we know that not all of my curves are perfect half circles or squares. We have graphs that are kind of weird shapes. So this is our first part of the fundamental theorem of calculus. And I can assure you that in Cal 2, again, those of you going on to Cal 2, you'll be using this for almost pretty much the entire semester. And despite the notation, all the symbols, you're actually going to see that we're actually just going through a process here. This is basically just saying get the antiderivative, plug in the upper bound, plug in the lower bound, and then subtract the two. Also note that it is important that it is upper bound minus lower bound whenever we plug it in. If you swap them around, that means your answer is going to be, instead of positive, it would be negative, or vice versa. All right, so using this new theorem that we have, we can finally evaluate a definite integral without the graph. So let's go into example, I believe this is technically example 2, because we did example 1 last time. Evaluate the following definite integrals. So I have 2 of them here. The first one is the integral from -1 to 4 of x cubed plus 2. Part B being the integral from 1 to 5 of the cube root of x squared. I'll give y'all some time for anyone to copy this down, and then we'll go ahead and get started. All right, so let's start on the part A on the left. Like I said, I have the integral from -1 to 4 of x cubed plus 2. The presence of that integral, the squiggly line that we're calling it, that's telling me I need the antiderivative. In particular, the antiderivative in respect to x because it's dx. So what is the antiderivative of x cubed? Yeah, we have x to the power of 4. Let me write this in red. So starting off, x to the power of 4. Is there anything else for the antiderivative of x cubed? Before we get that, are we done with the antiderivative of x cubed? What was our process for getting that antiderivative? We add 1 to the power. What was that second step? Power rule for integration. Yeah, so I add 1 to the power, and then I divide by the new power. Remember, exact opposite of the power rule for differentiation. Differentiation said multiply, bring the power down, subtract 1. Power rule for integration was add 1 to the power and then divide. All right, and then what you say was the derivative of 2? Yeah, we just have 2x. We don't really need to put divided by 1 because that doesn't really change anything. So I have the antiderivative, and I'm using the bounds -1 to 4. So again, that straight line, I'm indicating that I want to plug those in and then subtract, find a difference. So starting off with plugging in 4, for example, I'm just for notes, I'm going to plug this in directly. So plugging in 4, I get 4 to the 4th power over 4 plus 2 times 4. That's me plugging in my upper bound minus plugging in the lower bound of -1. So I'm plugging it into here. I've got -1 to the 4th power over 4 plus 2 times -1. This is me applying the fundamental theorem of calculus, part 1. All right, let's see what we get here. 4 to the fourth power. That's a large number. Let's see, we get 4, 16, 64, 64 times 4. What do we? Yes. So that would be 4 cubed, so 64. 2 times 4, we get plus 8. Minus negative 1 to the fourth power, we just get 1. Over 4, we get 1/4. Minus 2. All right, so 64 plus 8, we get, yeah, so 64 plus 8, we get 72. Yeah, 72. And then, so let's see, I'm running out of room here, but that's fine. 72 for the first part. Minus, you said negative 7 over 4? I'll take your word for that. Negative 7 over 4, and I can confirm that correctly. Making sure we're careful about our negatives and positives. All right, 72 minus negative 7 over 4. Minus and negative becomes plus. So what's 72 plus 7 over 4? 1 second. Let's see, what did y'all get? 73. No, sorry, 73, 3 or 4. Yeah, 73 and 3/4. What's that as a fraction, improper number? Let's just do this real quick. 72 times 4. What? 70 times 4, we get 2. What was that? For the final answer? 295 over 4. Let's double check. 70 times 4, we get 280. 280 plus 8, 288. 288 plus 7, yeah, 295 over 4. So we just evaluated this definite integral. I'll zoom out a little bit. So I did this definite integral and I got 295 over 4. What does that 295 over 4 represent? Position? Well, we're not talking about any physics applications just yet. What did it mean geometrically? If I had a graph? Yeah, area under the curve. But I want to be a little bit careful about how I word that. The way I'm going to word this is the net area under the curve. Does anyone have a idea about why did I want to say the net area under the curve and not just the area under the curve? Not that it is exact. So remember whenever we did that area under the curve with example 1, we had some parts that were positive, some parts that were negative. Yeah, the things that were negative, those were, well, negative. So whenever I added them together, it was technically possible for me to get, for example, a negative area. So it's more accurate to say I have a net area of this. If I wanted to say like total area, I might just say, ignoring the fact that some parts are negative, I'm just talking about all of that. They're positive, absolute values. All right, so I have part A complete. This is the part where we are starting to get into some calculation work, as you can see on the left. All right, let's go ahead and work on the right. Let me zoom back in on this so that we have it. I'll zoom out of all of this in the end so that we have it. So I have the integral from 1 to 5 of the cube root of x squared dx. Before I even try to get the antiderivative, what should I probably do to help me? Right now, we don't really know how to deal with it. What's the fraction? Yeah, I think I heard it from both of y'all. So it would be good for me to note that this is actually equal to the integral from 1 to 5 of x to, in fact, it turns out to be the 2/3 power. 1/3 coming from the cube root, It's 2/3 because it's x squared. So why does that help me? Why did I want to do that if I wanted the antiderivative? Well, because if I write it this way, we can actually just use our power rule for integration. It's x to a power. We know how to deal with those, just like how we did it here on the left. So I had to go ahead and find the antiderivative. We're going to use power rule for integration. Add 1 to the power, divide by the new power. So I get x. What's 2/3 plus 1? Yeah. Yeah. Both of y'all correct, 5/3. And then I divide by the new power. Just for the sake of writing, I'm going to indicate that I divide it by 5/3. And I like writing my fractions like that to show that that was originally on the bottom. And we're plugging in from 1 to 5. Before I actually go ahead and plug them in, it might be useful for me to clean this up. Otherwise, I end up with something that's really messy. How do I clean up dividing by a fraction? Yeah, all three of y'all basically saying the same stuff. To divide by a fraction, we do our keep flip change, or in other words, if I want to be a little bit more formal, we're multiplying by the reciprocal, the flipped version. 5/3 flipped is 3/5. So 3/5 x to the 5/3. And you can put your x on next to the 3 if you want, or you can put on the side. It means the same thing. Some people like putting 3x to the 5/3 all over 3. I mean, all over 5, sorry. It means the same thing. And I'm going from 1 to 5. Great. So I found an antiderivative. Now I'm going to plug in my values. Which one should I plug in first, 1 or 5? 5. We always plug in the upper bound first. So if I plug in 5, I get 3/5 times 5 to the 5/3 power minus me plugging in 1. 3/5 times 1 to the 5/3 power. So now I just got to clean this up. It's not going to be a pretty number. In fact, it's not even a pretty fraction, I don't think. So looking at this first part, I get 3/5 times 5 to the 5/3. So the way I'm going to simplify this is, well, the 3, I'm going to keep it there. There's not much I can do with that 3 in terms of simplification. What's 5 to the 5/3 divided by 5? We can clean that up. What would you say if I said 5 squared divided by 5? Then you get 5, right? Because you did 2 minus 1. So here we can do something similar. I can go ahead and I'll move this up for everyone to see. Here we get 5/3 minus 1. We can write that as 5 to the 2/3 power. Because here we have 5/3 minus the power of 1. On this side, we can keep it a little bit nicer. For example, 1 to the 5/3, 1 to any power is we have 1. So we have minus 3/5. So this is one way that we can clean it up. Again, not a very clean answer, but it is an exact answer. Another acceptable way that some people like doing it, some people might write it like this. 5 to the 5/3 minus 3 all over 5. Some people like writing it as a singular fraction and leaving it in that way. That's perfectly fine as well. At this point, it's more of a personal preference, as long as we have a more or less simplified answer. I guess you could technically factor out a 3 if you wanted to as well. So we have our part B complete. So that turns out to be some decimal, but I want the exact answer. So any questions about how we applied the fundamental theorem of calculus here? Again, we get the antiderivative, plug in the upper bound, minus plugging in the lower bound. I will say that the one thing that people often mess up here is not actually getting the antiderivative. People do mess up that sometimes, but getting the calculations correct. Like they'll get to this point and they might forget like a negative or a positive, or they say something like 4 squared is 8 or something like that. So we have to be careful with our calculations. All right, so we're done with example 2. That covers the fundamental theorem of calculus part 1. Now let's deal with the fundamental theorem of calculus part 2. So our second theorem for today, same title, but part 2. If my little f function is continuous on a closed interval, then the antiderivative, big F of x, which I'm actually defining here to be the integral from a to x of little f of t dt, is also continuous on that interval. Furthermore, I have this equation. And actually for this fundamental theorem of calculus part 2, the part that I'm actually going to care about is this right here. This is actually the part that I'm going to focus on. If I take the derivative of the integral from a constant, to x of my function, then I just get, it looks like my original function, but with x plugged in. I am glazing over a couple of things that I will explain in a bit. But intuitively, this might make a little bit of sense for us because we know the integral is like the antiderivative. This notation d dx is saying take the derivative. And we like thinking of the integral or the antiderivative, whatever you want to call it, and the derivative being opposites of each other. So in a way, it would seem to make some type of sense to say that whenever I take the derivative of the antiderivative, I end up with something like the original function. So again, this equation right here is what I want to focus on. Yes, sort of. You're going to see what I mean in a moment. It's kind of hard to explain without going too deep into it. Also, you'll see what happens in our example. All right, so fundamental theorem of calculus part 2. So let's go and jump straight in a couple of examples of this fundamental theorem of calculus part 2. Example 3, determine the derivative of this function. Let's say I get more interesting functions. Instead of just saying f of x or y is equal to something, what if y is equal to the integral from 2 to x of t cubed plus 1 dt? Notice here that I have an x or a variable as one of my bounds. So I will say that one way that you could do this is you could get the antiderivative and then use the part 1 of the fundamental theorem, plug in your upper bound, plug in your lower bound, and then take the derivative. You could do all that. But we like thinking of the derivative and the integral almost like opposites of each other. So let's go ahead. We want dy dx. I have y. This problem is basically telling me let's differentiate. The derivative of y is dy dx. Let's use red. Dy dx. So derivative of y, we get dy dx. And I'm basically just looking for the derivative of this expression. So I'm just writing this down for notes primarily. like so. I claim that we only have one more step here. The fundamental theorem of calculus part 2 essentially told me, again, very broadly speaking, is that my derivative and my integral cancel each other out. This will actually give me x cubed plus 1. Yes, it looks like I just replaced a t with x. Let's talk about why does this happen. If I looked at this originally, let's say I didn't have this written already, would you agree that we know how to get the antiderivative of t cubed plus 1? That's just power over rule. Yeah, let me move this aside. You don't have to write this next part, but it's just insight on why does this work exactly. Let's write this in blue. Yeah, we can do this. We get t to the 4th over 4 plus t from 2 to x. That's getting the antiderivative, right? All right, and then plugging in x and 2. If I plug in x, I get x to the 4th over 4 plus x, minus plugging in 2. I get 2 to the 4th over 4 plus 2. And then we can clean that up, right? This is what the function y is. But I don't want y, I want dy dx. So what would happen if I took the derivative of this expression? Derivative of x to the 4th over 4, we get x cubed. Derivative of x, we get 1. And what's the derivative of all of this? 0. That's why we actually end up with this here. Because whenever I deal with that integral from a constant to x, I'm just getting that antiderivative plus. And whenever I take the derivative of that, I end up back here. So for this example 3, it may look deceiving and that you should be doing more work, but the fundamental theorem of calculus is telling me, well, if I have a constant to a plane x, it looks like I'm just plugging in x for t. Exactly. We'll get to that in a second. In example 5, maybe. All right, so one thing I want to emphasize about the fundamental theorem of calculus part 2, this is from a constant as my lower bound and x as my upper bound, a plane x. So you already got ahead of me a little bit from example 5. I'll have to ask you to hold that question first. But again, this theorem works for a constant lower bound and a plane x is my upper bound. Let's go ahead and talk about the what if situations. But before I do that, any questions about example 3? Let's go ahead and do example 4 now. Again, let's get the derivative. I got y is equal to the integral from x to 5 of 3t sine of t dt. Am I allowed to instantly use the fundamental theorem of calculus part 2 here? No, why not? What's wrong with this integral? Yeah, remember earlier whenever I showed you all the fundamental theorem, it had an integral with a number as my lower bound and x as my upper bound. Good news is that this is actually a quick fix. Remember that I'm actually allowed to swap my upper and lower bounds if I just negate the entire integral. Yes. In other words, this is equivalent to me writing negative integral from 5 to x of, was it 3t sine of t dt. Remember that we're always allowed to swap our bounds, and we just put a negative in front of the entire integral. That's great for us. So now I can actually go ahead and find dy dx, not dt. So derivative of y, we get dy dx. Derivative of the right side, we have a negative. We carry that through because we know whenever we do derivatives, the coefficients go along. What is the derivative of the integral from 5 to x, 3t sine of t? 3x, yeah, 3x sine of x. We're done. In other words, I swapped the bounds to make sure it matched my fundamental theorem. My fundamental theorem says I had to have a number to x. After I do that, since I'm taking the derivative, the theorem tells me it looks like I'm just plugging in x. And here's a good thing about this. For that part, example 3, yeah, we were able to find the antiderivative, no problem. What if I ask you to find the antiderivative of 3t sine of t? Well, at this point, you don't know how to even deal with that because we've only done base derivatives and power rule for integration. All right, so that is example 4. Questions about this example 4? So example 3, we had a base case where we had integral from a number to x. Here it says, what if my number is on top and my x is on the... Now we can finally talk about what you were mentioning earlier. What if I don't have a plane x? And actually the answer to that is going to rely on an old rule that we've already covered in class before. Let's see. Let's look at this. I got g of x is equal to the integral from -2 to 1 plus 3x squared sine of t dt. Clearly, my upper bound is not a plane x anymore. If this was a plane x, then we wouldn't have a problem, right? It would just be exactly like example 3. But the question is, what happens whenever I don't have a plane x? And I claim that we've seen this situation before. Has there been a situation where we did derivatives, everything was fine, and then all of a sudden I said, what if I have something more complicated inside of my function? For example, we know how to get the derivative of, I don't know, if I ask you for the derivative of tangent of x, you could give that to me. If we remember the derivative of tangent, we get secant squared of x. But what was that rule if it was not just tangent of x? What if it was tangent of x squared? What rule did I have to use? Started with a C. You might be onto something. Yeah, the onion rule, or more formally, the chain rule. Because remember, chain rule said I can take the derivative of stuff where it's not just the plain x, but if it was like another function in place of there. So for this one, the way I'm going to start it off is, if I want to take the derivative, I'm going to start off by just plugging in the value. Again, I'm glazing over a couple of things here. What does the chain rule say we have to multiply by? What was my onion method saying? What of the inside? Do we multiply by the inside or the something of the inside? So we know that chain rule says that we did the onion method where we multiply by the derivative of the inner layers. Well, my inner layer here is 1 plus 3x squared. Yes. What's the derivative of 1 plus 3x squared? 6x. And I claim that we are done here. Because if this was a plane x, you would have just said sine of x. But it's not a plane x. We have a 1 plus 3x squared. In other words, we replace that x with an inner function. And our whole thing about chain rule was multiplying by the derivative of those inner functions.
We just chain rule the top.
Basically. And again, if you want to, you know how to get the antiderivative of sine. We know that the antiderivative of sine is negative cosine. And I could have done all this work. I would have eventually ended up here. But the fundamental theorem of calculus is almost like giving us a little bit of a shortcut here. So this is our final answer for this question. All right, so we have this example where I have a constant lower bound and a variable upper bound. There's one other scenario that I haven't really talked much about. What happens if my upper and lower bound both have x's? We've done a constant to a variable upper bound. We had a constant to whenever it's just not a plain x. What if I had something like this one? What if y was equal to the integral from 2x to x squared of, let's say, dt over 1 plus t squared?
What we just did minus the lower bound. So upper bound derivative of that minus the lower bound derivative.
You're along the right track. And I think you're essentially going to be correct. So I'm going to start this off, and we'll actually finish it off next time because I don't think we'll have enough time to go through the entirety of this. Well, we actually might. So before I even take the derivative, this integral is actually the same thing as if I wrote this. Let's see, what's the best way I want to write this? Let's do it from 2x to 0 of dt 1 plus t squared plus the integral from 0 to x squared dt over 1 plus t squared. Let's talk about why I can do this. Let's think about this geometrically. This is one area. This is another area, right? If we're talking about definite integrals. So, very broadly speaking, this is the area from here to here, 2x to 0. This is the area from 0 to x squared. Again, I'm being a little abstract here. So this gives me the first area. This gives me the second area. Well, this integral is the area from here to here. In other words, I'm able to split up an integral into two smaller separate ones if I wanted to, based off the bounds. In other words, these individual areas, these individual integrals are just an individual area that add up to the original one. So why would I want to do this? Why does that even help me? Just 2x. Oh, yeah, this one's just the board. 2x. So why did I want to split it up into two? Why would I want to make more integrals?
So that way you'll work on one integral and not both. Or is that right? They're separate.
So I have them separate, but why would I want to separate them? How does this benefit me more based off what we've done? Let's look at the bounds. Why does the bound from 2x to 0 help me compared to 2x to x squared?
Because then you're working with the bounds to
Yeah, remember our fundamental theorem of calculus says I want to work from a constant to some type of x. Well, by doing it this way, I have a constant in x. I do have to play around with this a little bit. Yeah, so let's see, we have a couple minutes left. Let's do this very, very quickly. So transforming this integral a little bit. Usually we like having x on the top. How do I swap my bounds again? Yeah, we make the entire integral and negate it. 2x dt over 1 plus t squared plus, and I don't do anything to the second one because we already have our constant on the bottom. Sounds great. Let's work with the first integral. First off, I have a negative. And fundamental theorem of calculus tells me I can start off by plugging in just 2x in for t. So I get 1 over 1 plus 2t squared. But the chain rule says I have to multiply by the derivative. Oh, sorry, not 2t, 2x. We're plugging in x, 2x, not 2t. Chain rule says I have to multiply by the derivative of 2x. So what's the derivative of 2x? Yeah, we get 2. So that is the derivative. And this should be, that's my mistake as well. This is dy dx. So this is the derivative of the first integral. What about the second integral? Well, I want the derivative of the integral from 0 to x squared dt over 1 plus t squared. I'm pretty much going to do something very similar. Yeah, so first thing it looks like I just plug in x squared almost. So 1 plus x squared. And what do I multiply by? Just 2x. Because I wasn't plugging in 2x for the second integral. Remember, we don't do, the way we do our chain rule is we just take the derivative of what's changed here. So we have this here. If I wanted, I could clean this up. Just for final answers, I'm just going to clean this up very quickly. I get, let's write this as negative 2 over 1 plus 4x squared for this first one. Plus, we can say 2x over 1 plus x to the 4th. And that is the derivative dy dx. I'll zoom out here. So we got the derivative of an integral where the upper and lower bounds had x's. All right, so any questions, comments, or concerns about anything that we've covered today? Again, this is the fundamental theorem of calculus. I would say between the two, part 1 is typically what you'll be using more often, but this part 2 is also very useful as we go through it. All right, so this was example 6 and our last example for today. Tomorrow, I believe we're going to talk about how do we start dealing with more complicated integrals, and that's going to be our last type of section. We're going to spend probably Tuesday, Wednesday, and Thursday, all 3 days on that last section, just so that we can get the algebra correct. All right, besides that, I will see you all tomorrow. Have a good, what's today? Monday.